Okay, so today's lesson is on 2-2, and we're looking at linear models. And many of you have done this stuff, so it should be kind of a review from Algebra 1, but we're going to go back over it again. And first of all, I would like to say that a linear function is a set of ordered pairs in the form of y equals mx plus b. If you remember, m is the slope and b is the intercept. So we are going to look at example 1, and this states jewelers emphasize that the price of a diamond is determined by cut, carat weight, color, and clarity. The table gives the carat weights and approximate prices in US dollars for 20 diamond rings. The data are graphed below. So here we can see that we have a scatter plot of various points that are in the table to the right. We also see that we have a line of best fit. And if you were to do this by hand, you would be basically taking a ruler and eyeballing it, so to speak, drawing a line through the center of as many points as you can, or in the center of as many points as you can. Okay, so part A says find the equation of the line through point 18 and 600 and point 32 and 1400, which relates weight and price. So we need to recall how to find slope. Slope is found by taking y2 minus y1 over x2 minus x1. And through these points above, we see that we have 2 points. I'm going to call this one x1, y1, x2, and y2. Okay? So if I were to put that back into my formula, I'm going to have 1,400 minus 600 on top. Those are my y points. And on the bottom, I'm going to subtract 0.32 minus 0.18. Okay, so if you put this in the calculator, you're going to get 5,714.29. Should be a 4. All right, we know that we are using y equals mx plus b. We now know m, and we have 2 points in which we can get x and y from. So I'm going to pick the first point, and I'm going to put 600 in for y, and I'm going to put 5,714.29 in for m. For x, I'm going to put 600, and I'm going to put plus b, because we need to find out what the intercept is of this line. 5,714.29 times 600 is 1,028.57. If we solve for b, we find out that b, and we do that by subtracting 1,028.57 from both sides. We're going to find out that b is negative 428.57. So our equation of the line, if I put in this for my slope, this for my intercept, is going to be y equals 5,714.29 x minus 428.57. So this is my equation. Part B says, interpret the slope of the line in context of the problem. Basically, it's saying that for every carat that is increased in the weight of the diamond, the price or the worth of it goes up by $5,714. Part C says, use the model to estimate the price of a 0.3 carat diamond ring. So all we're going to do here is actually put that in to our equation for X. If we take these two and multiply them together and subtract $428, we get $1,285.72. So the value of a 0.3 carat diamond ring is $1,285.72. Why is the model not good for predicting the cost of a 0.5 carat diamond ring? Well, if you put 0.05 into the model, it would be 1,714.29 times 0.05 minus 428.57. You're going to have a negative number. It's a negative $142.86. So we can't have a negative value for the diamond, so it is not good for predicting that. Also, if you go back to the graph on the page before, trying to get to it. There it is. We notice that at 0.05, that's going to be somewhere in here. If I take this graph and extend it down, you're going to see that it's negative here where it ends up being. So this also indicates that it's a negative amount or a negative value, and that's not possible in this case. Okay. Also, it says, why is the set of data not a function? Well, there are a couple places where we have different prices for the same amount of weight. So if you have two prices for the same weight, that means we have two y's for one x, and that means it's not a function. So example 1b, find the equation of a line that passes through points 1972 and 10.5 and 2004 and 9.8. So we're going to do the same way that we did in the last example. We are going to put it into our slope equation. So m equals 9.8 minus 10.15 over 2004 minus 1972. When you do that, you end up with negative 0.01 as your slope. So my equation is going to be y equals negative 0.01x plus b. Now I can use either one of these points again to find b. So I'm going to use this first one right here. Y is 10.15 equals negative 0.01 times 1972 plus b. And if I put that in, I'm going to have 10.15 equals negative 19.72 plus b. If I add 19.72 to both sides, I have a b of 29.84. So my equation of the line, if I use my slope and my intercept, it's going to be y equals negative 0.01x plus 29.84. In the diamond weight example, if you use the model to predict the price of a 0.3 carat diamond, you are making a prediction between a known value that was within our data set, in the range of our data set. And so this is called an interpolation. If you calculate the price of a diamond weighing 0.05 carats, because it's outside of our data set, it was lower than what we had before, this is called an extrapolation, or extrapolation. Data similar to the diamond weight example that is collected from sources such as experiments or surveys are called observed values. The values predicted by a model are called predicted values. The residual tells us how far away the data are from the model, or how far away the points of data are away from the line of best fit. So to find that, we're going to take the observed value we're going to subtract away the predicted value, and that will equal our residual. An example of this, if we're going to use the formula y equals 2,400 x plus 400. We have a 0.16 carat diamond ring sold for $507. Use the formula to find what it would be for the model. So if I do that, I'm going to have y equals 2,400 times 0.16 plus 400. I get $784. But the price that they actually had for it was $507. So if I take 507 minus 784, which is our predicted value, I'm going to have a negative 277 residual. I could do the same thing for a 0.33 carat diamond. That would be y equals 2,400 times 0.33 plus 400 Okay, so for this one I would get 800, actually we would get 1,192. And if you were to look back on the chart that's in your book, the actual value that you get is, the observed value is 1,417.50. If I subtract 1,192, I'm going to get $225.50 for my residual for that one. Okay, recall that when you compute variance, you add square deviations from the mean, and this is very similar to that because when we're looking at residual, we're taking a variation from the line. So similarly, when modeling data with a line, we can measure the variation from the line by adding the squares of the residuals. The sum of squared residuals is a statistic that measures the lack of fit. So if you compare two lines, the one with the smaller sum of squared residuals provides the best fit to the data. This looks very much like the variance that we were doing last chapter. If you recall, the variance was found by the sum of xi minus mu. So how far it was from the mean squared. And then we would take that and divide it by the number of data points. This is going to be very similar to that, except we're not dividing it.